We are starting from now our series on deep neural networks. Deep neural networks are used for classification, non-parametric regression, data generation, which is also called generative AI, and natural language processing. Traditionally, in machine learning, classification and non-parametric regression were the main applications. And for that, earlier other methods were used. For example, k-nearest neighbor, support vector machine, and kernel methods, and random forest. But since 2010, deep neural networks have been becoming increasingly more popular because in 2010s, 2011, 2012, and so on, deep neural networks won several major international competitions where they outperformed these other traditional methods for object recognition in images, for speech recognition, and also in games where they defeated the world champion in AlphaGo. This way, it was shown that deep neural networks are very versatile and, in fact, they can perform better than the other methods. And hence, they have become the method of choice in machine learning right now. In addition to having these extra applications of data generation and natural language processing, which the previous methods could not do. And in fact, these have become more popular methods right now. For example, ChatGPT is so popular and so effective and being used all over the world for many applications on which the previous method could be used. In addition, deep neural networks have some other advantages as well. For example, earlier, when these previous methods were used, before you will to use any of these methods, for example, random forest gain and so on, first we would do data processing. That is, one of the things would be feature extraction. In feature extraction, the input X, which we are going to know, which could be possibly of a very large dimension, for example, in images. First, you will do feature extraction, in which from X you will extract a smaller, much smaller dimensional data while containing most of the useful information before you will use any of these methods. That was done so that it will require less storage, less computations, and so on. This was very, very useful and was a standard preprocessing technique used in machine learning. However, feature extraction was a very time consuming and, in fact, costly affair. It used to require commonly the domain expertise and so on. But in deep neural networks, you can uh, feed to the deep neural network the original raw data itself. For example, the whole image can be fed to the deep neural networks, and the network itself will extract features in first few layers before it will start doing the object recognition. So this is one very big advantage in deep neural networks compared to the previous methods. Another very important advantage of deep neural networks is that you can incorporate prior knowledge in machine learning and you are training via the training sample. And in deep neural networks, this is done by what is called transfer learning. Again, we could not do that in k nearest neighbor and so on and so forth. The result of this is that after this prior knowledge has been incorporated via, let's say, transfer learning, you need a lot fewer samples to train and fine tune your machine. And of course, for less computational complexity as well. Therefore, these devices can actually be fed to even cell phones, for example, to the fine-tuning. So now we will start our study of deep neural networks. Neural networks are directed graphs on networks. which have nodes. V is the set of nodes, and edges. E is the set of directed edges. Directed edges means has a direction as well. And in addition, each edge has a weight. For example, if Eij is an edge in the set E, it will have weight Wij attached to it, and W will be the set of weights. If to the network X is the input, so which is a vector with component x1 to xn, it will pass through the input layer. So this is the structure of the network. X is the input vector with an Rn. Y is going to be the output of the neural network, may again be a vector in Rm. The neural network has layers. It's organized in layers. There, the first layer, called the input layer, we are going to call it 0th layer. You feed the input to this layer, and then the data from input layer goes to the first layer, then to the second layer, and third layer, and so on, till it goes to the output layer, which we are going to call Tth layer, and from there we'll see the output out of the neural network. So nodes in layer first will be connected only, will be feeding data only to the second layer, and second layer nodes will be feeding data to third layer, and so on. The nodes first to T minus 1, which are the nodes inside the network, are called hidden layers because these are not exposed to the outside. Input layer gets the input X. Output layer sends the data out, and hidden layers are inside. In this case, there are T minus 1 hidden layers, capital T minus 1, and there's an input layer and an output layer. If in the network there is only one hidden layer, then the network is called shallow neural network. Otherwise, if there are more than one hidden layers, it is called deep neural networks. Today, we study usually deep neural networks, but we will, as a part of our study, consider shallow networks as well as a special case. Each node in the hidden layers is of this type. It has inputs coming from the previous layer, nodes from the previous layers, which we are going to denote as Z1 to Zk. So these are the inputs coming to a node in, let's say, layer T minus 1. All the data coming to the node adds up. So this is summation sign. And then it passes through a nonlinear activation function, which we are denoted by this signal. So after this, the data goes out of the node. Output of the node is denoted by Z. So therefore, this output Z is equal to sigma, this sigma here, which is the nonlinear activation function, which operates on the summation of all the inputs come to the node. After this node, the output that you see Z goes through the nodes of the next layer. So this was node in T minus 1 layer. Then the data will go to nodes in the Tth layer. So this is the output from the node. And then the output goes via these edges to the nodes of Tth layer. The edges have weights W1 to Wk. So the Z coming in here, when it goes through this node with weight W1, it becomes multiplied with W1. So we get W1 Z, and this is what is fed to the next node here in layer T. Similarly, WKZ goes to another. So these are the inputs going to K different nodes at layer T. So this is how the network is organized. These are the nodes of the hidden layer. The input layer is simpler, where the input data comes. Xi is the ith component, the input. It goes to the ith node in the input layer, and then nothing else. For example, because there is only one input to this, there is no summation required, and there is no activation. But so this Z is simply Xi, and then it gets multiplied by the weights to go to the nodes in first layer, next layer here. So this is how the data enters the network. At the output layer, the nodes are again simple. This is represents the output, a node in the output layer. This is the data coming from different nodes in the previous layer. It gets added, and then it's just output as yi at the output, ith output node in the output layer. We mentioned about the activation function. This is a nonlinear activation function in each of the hidden nodes. The common activation functions used are the following. Sigma that we noted with. First, we should mention that sigma should be a nonlinear function. If we keep this sigma to be linear, then the mapping x from the input to the output y, so x and y are group vectors, will become linear. And of course, linear functions are useful in practice, but they are very restrictive and not sufficient for most of the applications. Therefore, the activation function needs to be non-linear. Also, in principle, these activation functions at different nodes in the hidden layers can be different, but it's a usual practice that we choose one activation function for all the nodes. And the possible activation functions are to follow. One is sign function. Sign function is sigma a equal to 1 if a is greater than or equal to 0, is equal to -1 if a is less than 0. Is plotted here on the left hand side. Second is sigmoid function. This sigmoid function is 1 by 1 plus x minus x exponential minus a, and it's plotted here on the left hand side. There is a hyperbolic tan also, which is again denoted here, is tan a is equal to 1 minus exponential minus 2a divided by 1 plus exponential 2a, and it is plotted here. This looks somewhat similar to the function here, but of course, the slopes are different. Then there is this called ReLU function, rectified linear function. This is equal to max of 0 and a, and it's plotted here. For minus a is 0. For positive a, it's equal to a. It's just linear in this direction. And leaky ReLU is just a modification of it. Sigma is max 0a, this is this part, plus alpha into minimum 0a, where alpha is a small positive constant. So what you see is, and when a is positive, it's equal to just a, as in if a is negative, then it becomes alpha into a. These functions, so for any deep neural network, we'll choose one of these functions. The first function is discontinuous and at 0. The ReLU is continuous, but it's non-differentiable at 0. And sigmoid and tan, hyperbolic tan are actually differential functions. And of course, except ReLU and Leaky ReLU, the others are bounded as well. These properties are important, and as we go along, we will comment on these properties later. So the neural networks that we have just talked about, these are called feed-forward neural networks. They have no loops or cycles in the network. Data comes from one side and goes through the other side, and data goes from layer 2 to T+1 and so on. It never loops back. But there are also neural networks which have loops and cycles, and we will discuss those neural networks later. Feed-forward neural networks with no cycles and loops are most popular. If you fix the waves, W's, and the signal activation function, then the overall neural network behaves as a Westminster function, which we can denote f. X is the input, y is the output, so we can say fx is equal to y. An important property of neural networks is that these are universal approximators. What it means is you can take any function f from Rn to Rm, any function. It can be arbitrarily closely approximated by a neural network. So this explains that this is a very important property because this mentions that this overall set of neural networks is very rich. And this is important because as we go along, different neural networks at different times will be used to approximate, classifiers, regression functions, and so on. If you have a very flexible initial structure of like deep neural networks, then we can train it to be close to any function that you may be using in real life. So now we explain and elaborate a little bit more on what this universal approximation property of deep neural networks is. Here we are going to limit ourselves to binary functions. And for that, let me first explain the digital gates like AND, OR, and NOT gate, how these can be implemented by deep neural networks. Let's take input X, which has component Xi, I is equal to 1 to N, so N components, and these are binary. So Xi takes values in 0, either 0 or 1. But here in our implementation, 0 will be presented by -1. So Xi will take value either -1 or 1. And if we want to take output y as an AND of x1, x2, and xn. So once we have written 0 as -1, then the advantage is that an AND expression between x1 and xn can be represented by this mathematical function, sine of summation I is equal to 1 to n xi plus 1 minus n. And remember, sine of A is 1 if A is positive and -1 if A is negative. So you can very easily check that this mathematical function is actually representing the AND function between these binary variables. And on the left-hand side, I have denoted the neural network that represents this AND function. This is the input layer where the N components are adding in, and there is one more node at the input where only one gets added. It's a constant. This is a node, one node. We need only one node at the next layer, hidden layer. So I have represented that node the way it should be, and the activation function used here is the sine activation function, which is this function here itself. So first N components get multiplied by 1. So these are 1 are the weight vectors, these edges. And the last edge, the weight vector is 1 minus N. All these things get added here. So then you see output of this is simply this quantity inside, and then sign is what the sign that we needed here is doing here, and this becomes the y. So this simple neural network denotes the AND operation in binary functions. Next, let's look at the OR function. So why the output is OR of n binary functions? This is the OR operation, x1 or x2 or 2 xn. Now, if any one of these is 1, then y should be 1. If all of them are 0, which is here going to be represented by -1, then output here should be 0 and here represented by -1. Now you can easily check this binary operation is same as this mathematical operation of putting sign function on these terms here. And corresponding to this, you see this is the neural network. At the input, you feed in x1 to xn, and there is 1. And to the next node, the weights are 1 on first n components. In the last one, now there is n minus 1, because this is the n minus 1 that you need here. They get added and put through a sign function, you get y. This is exactly the OR function we need. Next is NOT function. So here, this NOT function, here there is only one variable, put a NOT. So if it is 1, not 1 is 0. If it is 0, not 0 is 1. And of course, 0 is represented by -1. So therefore, in this notation, it will become y is equal to -x. And this simple neural network does this operation. We know that any digital circuit can be implemented by AND or NOT gates. These are universal gates in digital networks. So showing that each one of these gates can be implemented by a neural network, we have shown that any Boolean function f from 0, 1 to the n, so it has n components, to 0, 1, can be implemented by a combination of the neural networks that are given here. And if you have binary function, vector function, 0, 1, n to 0, 1, m, this function f can be represented as m function. F is f1 to fm, where each of the fi's is a function like this. And as we have seen above, that any one of these fi's can be implemented by a neural network. So to represent this binary vector function, this is the neural network we'll need to have. This is the input, feed x vector to the input, and each of these boxes are the components of the neural network. For example, this will be implementing f1 function and so on, and this will be implementing fn function. Together, this neural network implements this binary vector function 0, 1, n to 0, 1, m. So this way we have shown that any binary function, vector functions can be implemented by neural networks. This is one stage in showing that neural networks are universal approximators. In this sense, what we have shown is that any binary vector function can be implemented by neural networks. In next lecture, we will continue on this.